It's a shift in AI where you can train a model through a phase called pre-training using something called self-supervised learning. So the shift is that you really don't need to give it any labels. Here you just give it data, and the network learns patterns and relationships within the data itself. So what this enables is it basically enables building AI applications much faster. So you can imagine that we can actually accelerate scientific applications by having these AI foundation models.
Hi, I'm Stephanie Tumampos, and you're listening to Down to Earth, the show where we talk to incredible geoscientists about their science and its impacts on our planet. This season, we're exploring the many ways we can harness the power of artificial intelligence to learn more about our world. I'm also on a personal quest to discover if AI will be more of a help or more of a hindrance to our work as geoscientists. Now, you might have guessed it already, but today, we're taking a look at foundation models. Foundation models are large-scale, general-purpose AI models that can be fine-tuned for specific tasks like climate modeling. But what makes them so special? Well, today, we're chatting with researchers from NASA and IBM to find out what the hype is all about. This episode of Down to Earth is brought to you by the Geoscience and Remote Sensing Society's technical committees. As part of the world's leading professional association for the advancement of technology, the GRSS technical committees are innovation hubs, bringing together experts from around the world to forward cutting-edge geoscience research, development, and applications. To learn more and be part of the premier community driving the future of geoscience and remote sensing, visit grss-ieee.org and join a technical committee today.
I think people equate foundation model equal to ChatGPT. The foundation model there is GPT, and ChatGPT is just an adaptation of GPT to do conversation, right? So GPT has been used to do codecs, to do coding, and multiple things. So one GPT model enabled so many different kinds of capabilities. I think the question for us was, hey, can this apply on scientific data?
This is Dr. Rahul Ramachandran, Senior Research Scientist at NASA Marshall Space Flight Center, where he leads the Interagency Implementation and Advanced Concepts or IMPACT team. His research interests span a range of topics, and he's contributed his knowledge and research to fields including data science, informatics, and AI and machine learning.
We had a very cool moment in our project, and I remember that it impressed many people. When we were training the weather and climate foundational model, we took the world map and we removed 99% of the pixels. And the model was in a position of reconstructing that with a minimal error. And for me, it was like, I've been doing AI all my life, right? That's my professional career. And it really surprised me in terms of how much the model was able to learn and the power of reconstructing data with this level of precision. It was amazing.
This is Dr. Juan Bernabé-Moreno, Director of IBM Research Europe for Ireland and the UK. With over 20 years' experience in the machine learning field, Juan is responsible for accelerated discovery for climate and sustainability across IBM research, which focuses on the convergence of AI, quantum computing, and hybrid cloud to advance environmental sciences. In 2023, NASA and IBM began a special partnership to use foundation models developed by IBM to discover insights in NASA Earth science data. Less than 7 months later, the team released the largest ever open-source geospatial AI foundation model on Hugging Face. This feat not only provides scientists with an effective tool for estimating things like past floods and wildfires, but it's also the basis for developing additional case uses in areas like climate prediction. Before we get into the interview, we need a basic understanding of foundation models, also known as general purpose or GP systems. Basically, they are AI models that are pre-trained on a broad set of unlabeled data. When you feed a foundation model this unlabeled data, it can piece together patterns and relationships found within the data, which forms a general base of knowledge. From there, the model can be customized to perform different tasks. It can also take information about one situation and apply it to another. Unlike AI emulators or narrow AI systems, which are AI models that are trained to perform one task on one dataset, like predictive text or image recognition, Foundation models can process and analyze many types of raw data. They can also learn from new data to update their predictions. This makes them very useful when it comes to the geosciences, especially since the Earth and its systems are constantly in flux. Foundation models are certainly an exciting tool, but as we'll learn in this episode, they come with a catch. Despite their incredible potential, building many different foundation models might not be the best move. Let's learn more. Okay, today we're talking about foundation models. And before we dive into the specifics of the NASA-IBM collaboration, let's talk generally about these models. How do you build a general use foundation model? Can you walk us through the thought process?
For us, it always starts with science. You have the science expertise to define the problem, to frame the problem, to define the scope of the problem, where the bounding box is, what we should do and we shouldn't do. So it's a non-trivial task trying to figure out how to build a foundation model that would be useful to a wide variety of science users. So we start with science use cases to understand. We take a broad range of these use cases so that we can serve wide variety of science users that use NASA data all the time. And from those use cases, then we go back and define requirements that are then fed into the design of the architecture, what data set we use for pre-training, what it should be able to do. So it's not taking something that is off the shelf and trying to use it. It's basically building new architectures that are adapted for that particular problem.
Right. And who is usually involved in building a foundation model? Like, who are some of the team members?
You need AI/ML experts. So this is basically, I would say, 5% of people who have AI/ML expertise who can actually design new architectures that would be needed. Then you need data engineers to move the data, pre-process and do all the data munching that is required. You need machine learning engineers because once you have the model, you need to then build these use cases, help the science researchers build these use cases or adaptations on it. You need infrastructure expertise because you have to scale. You do your experiments on smaller amount of data with smaller number of nodes, GPU nodes, but when you have to build it up and scale, you run into issues of scaling. So you need people on infrastructure side to help out. And I think one critical point that we'd like to eventually see in the future is the trainers. We should not build these things in vacuum. We need people who can train the community on how to correctly adopt and utilize these models. In an ideal situation, that would be the team that is required.
I would like to also emphasize the rigor. The scientific rigor is very, very important because it's all about credibility and the utility of the models in the end.
Yeah, I think the rigor is absolutely right. We are trying to have the same scientific rigor in these AI models as we do with our data sets or any physics-based model that we release. I think that is the interesting thing. The distinction between the language model and the science models that we're trying to build is that right? Typically, on the language side, it is understood that what the model is learning is statistical patterns between words, right? And then you are using that. But on our scientific data, what we're trying to understand is what is it learning? Is it actually learning underlying processes, underlying physics? That is the big question. If we can show that it's learning some of the physics, I think then we have truly a new approach to doing data-driven modeling in science.
You both mentioned rigor. How do we guarantee the rigor? What are the challenges here?
That's a very complicated question, right? Because it's a multifaceted question as well. We've been describing our world, right, with physical equations. But these physical equations, they are, in the end, models to explain the reality and the world, right? When we adopt a completely different approach, which is like, let's learn from the data. Obviously, we try to make this data compliant with these physical equations. Sometimes you have some deviations. And then you start asking yourself, these deviations are because actually we are reflecting different aspects of a reality that we couldn't capture? Or are these deviations because of a measuring instrument? Or are these deviations? So that alone is a very interesting research area. But let's go back to more practical cases. There are more practical cases where you have benchmarks and you have baselines. For example, what we do a lot is like we look at how bespoke models, not foundational, but bespoke models just trained to do something very particular, with a very particular, well-defined data set, how they perform versus the combination of the base model, or the foundational model, with the fine-tuning phase, right? So where we take the foundational model and we specialize that to solve this particular task. We are entering, as we do it, a new territory. It means that we do have some benchmarks here and there, but there's no general benchmark. And we are engaging with the community as well to develop several projects for that, right? One of them is, for example, GeoBench, where we try to establish for each and every potential downstreaming task to establish some validation criteria. I think what's important is also to understand when we talk about validation what we mean, because the advantage of a foundational model is not only reaching similar performance, but also the ability to generalize. And in geospatial sciences is very important because with a few localized, well-sampled training areas, you can really create something with very little effort, and this model can generalize for the whole world.
Right. And at what point in building a foundation model do you say, okay, it's ready. We've done all the checking we can. It's ready to be out in the world.
So from my science perspective, it is basically when we get to a stage that we feel confident that the science community can use it, right? It's like any other tool or data product that we build out, right? So the process that we are looking at is, when we build a model, we look at 3 releases. First release is provisional, open it up, get feedback, then incorporate the feedback into your next release. Update the next release, open it up, share it, get feedback, and then you get the final release. Hopefully by the 3rd release, you've got all the major things that the community needs. It'll never be 100%, will meet everybody, but if it meets 80%, I think it's good enough.
Just to add on that, the role of the community is critical, right? It's so important here, just because nobody can do it alone. And acknowledging the role, for example, of academic institutions, other type of institutions, smaller players, startups, and so on. IBM, Meta, and other companies, NASA is part of that. We created the so-called AI Alliance, and the AI Alliance takes care of these questions, right? For example, how to make sure that enough is enough in terms of trainings, like the saturation point. What's the right way of benchmarking foundational models? What's the right way of coming together and one partner provides computing power, the other partner provides skills, the other partner provides data, and we innovate in the open for the benefit of everyone. I think that's very refreshing. I've never seen that in the history of computing. So it's really, really new. And it probably explains how important what's happening in AI today. These many big companies, Red Hat, the National Science Foundation, I don't know, Oracle, many big names all around the world, they are really committed to innovate in the open.
So you mentioned the word collaboration, and the reason you're both here in today's interview is because of this incredible collaboration that NASA and IBM formed back in 2023. So tell me about it.
Well, IBM has been working on this Gen AI technology for many years already, way before the GPT moment, and we've been working over many years with NASA. I think we are very like-minded organizations. And one of the things that I'm really in love with when it comes down to working with NASA is this spirit of open science and the spirit of creating impact. Is all about lowering the adoption barriers. Like, we gather so much data on a daily basis, yet the use that we make of this data is limited because of many factors, complexity, computing power. So in 2023, we decided to engage on a pioneering effort consisting on this amazing data treasure, right, which is kind of a joint venture between NASA and the European Space Agency, creating this harmonized Landsat Sentinel data to turn this data treasure into an AI representation, into a foundational model. And by doing that, to really enable the scientific community to start leveraging the power of this data, specializing the model for many applications. And that's probably how we started the collaboration on foundational models with Rahul's team.
Yeah, I think, when we started this collaboration, we were actually only looking at language models. We were trying to figure out, hey, can we build language models for science specifically to help out in tasks? But I think this is an example of having, bright people from both organizations working together. And once they started discussing ideas and things grew from there, the question was, hey, why can we not try it on scientific data sets that sit in our archive? We've got 100 petabytes of data. Most of them are sequence data. There are different modalities. Can we apply the same approaches?
After the break, we find out the answer to Rahul's question, and we'll also learn about some of the exciting outcomes of this important collaboration. I know you're also dying to find out why these scientists don't see merit in everyone building their own foundation model, so we'll cover that too, right after the break.
Want to be at the forefront of geoscience and remote sensing innovation? Then join one of the Geoscience and Remote Sensing Society's technical committees. With 8 committees to choose from, you'll find your niche. From earth science, informatics to data fusion and climate technologies, our committees are driving progress and advancing the state of the art in geoscience remote sensing work. Through our networks, you'll collaborate with global professionals, participate in cutting-edge research, and apply innovations to real-world challenges. Enhance your career, expand your network, and contribute to a better tomorrow. Visit grss-ieee.org and join a technical committee today.
Welcome back. Today we're speaking to Dr. Rahul Ramachandran, Senior Research Scientist at NASA Marshall Space Flight Center, and Dr. Juan Bernabé-Moreno, Director of IBM Research Europe for Ireland and the UK. Together, these scientists are leading an exciting venture between IBM and NASA with the goal of finding and testing new applications of foundation models to provide an easier way for researchers to analyze and draw insights from large NASA datasets related to Earth processes. As Rahul explained earlier, when the collaboration first began, the team started with training a model on over 300,000 Earth science publications. The goal was to thematically organize the literature so it would be easier to discover new knowledge. Even before this experiment was successfully completed, the team was inspired by the power and potential of the foundation model and began wondering if they could try it on scientific data. As many of the scientists on our podcast have mentioned, Earth observation data is challenging to use in AI models due to the different modalities of data. Basically, it's hard to combine all the different data sources, so the possibility that a foundation model might be able to do this work seamlessly and quickly was very exciting to the NASA IBM team. The result was the HLS Geospatial Foundation Model. Released on Hugging Face in 2023, the model supports estimates in land use change, monitoring natural disasters, and predicting crop yields, among other capabilities. What's more, it is the first open-source geospatial AI foundation model for Earth observation data shared by NASA. This is a huge step in NASA's work to democratize access to and application of AI for generating new innovations in climate and Earth science, and IBM is right beside them supporting this open access goal. Except, as I mentioned earlier, there's a catch. Let's discover just what this entails. So, tell me about the outcomes of this incredible collaboration. What have been some of the successes?
Probably is the very first outcome is the learning aspect. We were kind of pioneering this effort with a lot of uncertainty related to infrastructure, architecture, data, understanding of the data, understanding of the results. So it's been a journey. But in terms of outcome, right? I would separate 2 categories. First of all, it's like we managed to put together and we put in the hands of the community. The very first foundational model, the Prithvi 100 million parameters based on HLS data, is being deployed on Hugging Face. So everyone can take it and can start specializing that for many, many use cases, right? I think that's a great deliverable. And I would say also I've seen that for real, right? Helping in emergency scenarios is how quickly you can develop that. So how data efficient and how quickly can you specialize the model to solve a particular problem. Compare with a bespoke approach. We are working, for example, with the government of Kenya, and they were facing an emergency situation due to flooding. And they reached out because we were partnering with them for deforestation use cases based on this particular model as well. And we managed in a matter of 1 to 2 days to generate the right insights in terms of where to put the right shelters for the flooding, which critical infrastructure has been impacted, helping the Red Cross manage the emergency situation. And they were very, very impressed by how quickly we managed to really create these specialized versions of the model. Usually, to train this particular model in a bespoke manner, it could have taken way longer. So these 2 days is like, including all the interactions with all the parties involved. And so we going back and doing some blah, blah, blah. So it's like, it was very, very, very quick. And we were surprised ourselves by how versatile these models are and how quickly you can really specialize the models to solve a very particular problem. Alongside this one, we've been educating the community. The foundational models, they are in the end a capability, but they are not the solution, right? You need to really take it and adapt it to your problem, specialize that, and see how it cuts in relation to the requirements of your use case. So it's, for me, very, very important to create the assets so that the community can start working on their own.
Rahul, do you have anything to add?
Yeah, sure. I think first and foremost, exchange of knowledge has been immense in this partnership. We've learned a lot from IBM research. Hopefully, they've learned something on the science side from us on it too. I think when we started this thing, there were skeptics everywhere of the value for this. Definitely within NASA, I'm sure within IBM too, we had to convince a lot of people because, as this work expanded, we needed additional resources. So I needed results to show to my management that, hey, this is really changing the way we can, infuse AI into scientific processes. And this will have a major impact on humanity and society as a whole, right? I think so. We needed to show results on that. And I think we've done that. The HLS Prithvi Foundation Model is a really good example. Even though it was a proof of concept to justify to ourselves whether it's worth putting in resources, just the fact that we made it openly available and it got picked up by people. I got an email, a really nice email from a group in Africa where they used it to do locust breeding ground detection. They said they were unable to do it till they got the model combined with HLS data. Not only that, they started building tooling around the model. That's the kind of things that you want to see, right? That's the whole power of open source and opening up and letting community take it and push it as far as they can. That kind of examples are instrumental in us, realizing that, hey, there is power to this. And it is our responsibility to make these as scientifically rigorous as possible so that the community can use it with confidence for their applications.
And this year, the team expanded beyond the HLS model to release the Prithvi weather climate model. Why the focus on climate next?
Yeah, I think the initial idea is like Prithvi means earth, right? In Sanskrit, it means earth. The goal is Prithvi is a family name, and then we'll have foundation models encompassing earth as a system. So HLS was the first one. HLS focuses on land use environmental monitoring applications, right? So it is focused on optical remote sensing data, but hopefully we can add, SAR to it. Then the next evolution was atmosphere, right? So that's why we went with weather and climate. So hopefully we can build out the major subsystems of Earth as a system and then have foundation models for the entire family of Prithvi. And then people can use it in those specific domains or combine them to use them to do, system level science and applications.
Let me add something also very important. The beauty of foundational models in this context is you can have a weather over many, many, many years, and you can end up learning beyond the weather scale, time scale, so you can really go into the climate scale, right? To me, that's very innovative, first. And second, it's really new. We didn't have such an instrument before to understand the weather in the context of climate, and then take a climate model and downscale it to weather. So it's something very unique, very versatile, and we are just scratching the surface in terms of what we can do with that. That's one thing. And the other thing is like the ability to combine these models that Rahul mentioned before, right? And one example that we are trying to explore is the formation of urban heat islands and the impact on health. And we are doing that, for example, with the government of South Africa. And there what we see is like, while we can take the HLS model to fine-tune that to predict the land surface temperature, the data that we have from the weather is too coarse. So we can use the other foundational model to make it much more granular, so that the insights from one benefits from the input from the other. So, and that's just one example of the possibilities ahead of us. So it's a very, very thrilling space.
So, my first thought is that this model is very timely right now, especially when it comes to climate change. I mean, summer here in Germany has been experiencing rather extreme and dynamic weather conditions. Like, we have had intense thunderstorms every week with flooding and hail in many areas of Bavaria just this summer. And we just had early snow in September in the Alps. So, being able to have the tools to predict these weather patterns is going to be important. And secondly, you've both touched on this with your examples, but the usefulness of these models, both the HLS and the Prithvi climate model, are already impacting society. So I want to dig deeper here. What factors around social impact do scientists need to consider as they research and, more importantly, deploy foundation models?
I think for science community to use these models with confidence, they need to understand what the model has learned. So I think there is still a large area of research in that whole, like, how do we, break open this black box so that people can probe these models and figure out what it has learned and what it has not learned. I think that is very important. I think the other thing that needs to be done is this notion of fitness of use. It is a tool in some ways, right? You're basically giving a foundation model. It is on the science user to know whether it is applicable for your particular application, right? So that fitness of use, how do we characterize these models in a way that people can make those decisions really quickly and correctly, right? Also, the notion of provenance on the model is very important. So it is really important to understand, okay, I'm picking up this model, but it has been pre-trained on a data set that is scientifically accepted by the community to use. Because there's a lot of data out there, like you don't know what went into it, right? So the provenance is a really important thing.
Just to add that the whole topic of governance. Why governance? Because governance for me encompasses many aspects. It's the rigor that Rahul mentioned before. Then transparency is very important. It's transparency in terms of open sourcing. What are the weights? Why? How did we train that so that everyone can understand how these things came together? Then something that for me is critical as well is it only works if people adopt it. Otherwise, it's really investing too much upfront, right? Because you pre-train, and pre-training is costing a lot of GPU, time, resources, and energy. So creating the right tools to enable the adoption, that's critical as well. And having the right platforms and the right size of the models. It's not about going trillions for the sake of trillions. It's like we need to be more clever also on how to operate the model. And that's probably another point that's very important. We are going to come to a point in the next years where fine-tuning and using the model is going to be way more important than just pre-training the model, because we are going to have pre-trained many of these models, and they're going to be pretty good, right? I think we really need to start looking at how to lower the energy consumption and how to lower the entry barrier at the inference time when you really use the model. That's going to be very, very important in the future.
I think the energy part is a really interesting point Johan has made. I think the key challenge here is, when we started on the foundation model for science, it wasn't a buzzword. Now it has become a bit of a buzzword now. And everyone wants to build a foundation model, which I think is to me, it's a little scary. It was rather unproductive that every group is trying to build a foundation model, because it's a waste of resources. There's a major impact on the environment trying to build these models, which take up, so much compute and so much energy. The language model that we build is a small encoder model. I think it's 100 million parameter compared to GPT, which is billions. The power consumption to build that model was about 400 houses for a day, in the US houses. So you can imagine if you start building these huge models and everybody starts building it, I think we are doing a major disservice to the community that we serve if we start doing that. So I think the better approach is, like what we're trying to do is collaborate. Every model that we built This is not just IBM and NASA collaborating. We have other partner organizations that we bring in for each of these models. And we say, join forces with us, contribute where you can. So that's the approach that we want to take, is an open collaborative approach where we bring everybody together so that we build something that is more community-driven, developed, and adopted.
That's a very powerful message, Rahul. And I think it speaks to the success of the NASA-IBM collaboration too. Thank you for that. Okay, this season, we're exploring whether or not AI will be more of a help or a hindrance in geoscience work. So what are your thoughts?
I believe, and I'm positive, that what's next in AI, not only the ability to train foundational models and to really democratizing access, so you don't need a big class computer to specialize a model. And so what to me is enough reason to believe that AI is a blessing, not a curse for geospatial, right? Beyond that, what's coming next, which is all the agents-based workflows where you are going to be interacting with these models using an agentic workflow. And this agentic workflow is going to help you plan, execute, orchestrate different models actually to achieve a particular task. It's going to change the way that we run geospatial. I'm positive about that. And we are seeing some examples already, so I'm extremely positive. So a big, big blessing versus a curse.
Rahul?
Yes, I'm on the optimistic side. I think, as Juan was mentioning, if we do it right, it's done in an open, transparent manner. We're inclusive so that we don't have haves and have-nots, which can become a major disparity in the future. People or certain groups have the capability and some don't. Those are the things we want to avoid. If we can build a future where it's inclusive and everyone can reap the benefits, I think it's going to be a major shift in how we do science. So I feel very optimistic that with these models, we'll get close to fully extracting insights from the petabytes of data within NASA.
I believe that despite remarkable advancements in AI and the exciting models that continue to enhance our understanding of the world, we are still only scratching the surface. There's much more to discover and numerous resources we can leverage to push the boundaries of the current technology. And leverage is the operative word here, because as Rahul and Juan mentioned, we can't all run out to build our own foundation model. They take too many resources to justify every scientist and lab having their own. So how can we leverage the existing foundation models we do have to extract important insights from the vast amounts of data being produced daily? And how can we share existing resources across scientists and labs to maximize resource use? I believe if we can find the sweet spot between resource use and modifying models, then AI will be a huge help in solving our most pressing challenges. In our next episode, we dig further into this concept of collaboration for real-world change. To learn more about the NASA-IBM collaboration, check out their Prithvi Foundation Models on huggingface.co. You can also search for the Prithvi Weather Climate Model on both NASA and IBM's websites. Don't forget to follow and rate us on Spotify and Apple Podcasts, and go give a like to our sponsors at IEEE_GRSS on X and Instagram, and IEEE Geoscience and Remote Sensing on Facebook and LinkedIn. This episode was produced by Nicole Bedford from Nicole Bedford Films, with help from me, Stephanie Tumampos. Graphics and design by Mylene Briggs of Kila Media. And a special thanks to Manil Maski and Fabio Pacifici for their support. I'm Stephanie Tumampos, and you've been listening to Down to Earth.